Hello, everyone.
We
I
can.
want to welcome all of you to this webinar. This is being hosted by Pharmacometrics Africa, Nigeria chapter. So I want to really appreciate the Pharmacometrics Africa for providing this platform for us to have this webinar. Been a long time, we've been looking out for a moment to institutionalize pharmacometrics in Nigeria, and we are taking this short step to make sure that pharmacometrics become institutionalized in Nigeria. So I want to appreciate everyone for joining the webinar. Um, at the background, I want to appreciate Gabriel from Pharmacometrics Africa and also Professor Colin Pinlay for the support that have been granted to us. So I will hand over to Thomas Uchiko to kindly introduce our guest speaker for today.
Thank you so much, sir. Our speaker today is Babajide Shenkoya. He holds a Bachelor of Pharmacy degree and a Master's in Pharmaceutical Chemistry from Obafemi Awolowo University, where he focused on statistical and computational methods at the Translational Pharmacokinetic Research Group that we call TPRG for short. He's currently a doctoral candidate at the University of Maryland School of Pharmacy. His research interests include applying quantitative approaches, particularly pharmacometric techniques such as non-compartmental analysis, population pharmacokinetics, and PBPK modeling and clinical trial simulations to address critical questions in clinical practice and drug development. So today we have Babajide with us, who will be taking us on fundamentals of pharmacometrics, just basically taking us through the basics of pharmacometrics. So the next voice you will hear now will be that of Babajide Shenkoya. Over to you.
Thank you very much, Chuko, for the kind introduction. So I'm now going to share my slide with everyone. Can you hear me okay?
We can hear you just fine. And
all right. So I would like to start by thanking the organizers for inviting me to share my insights in this webinar series. Pharmacometrics Africa is doing amazing work in raising awareness and training across Africa, and I really appreciate their continued efforts. And let me use this opportunity to start by mentioning that, you know, a few years ago, just like everyone here today, I attended webinars and workshops like this one, you know, most of them facilitated by Pharmacometrics Africa. And it was right from those moments that I developed a strong interest in pharmacometrics. And ever since then, I have not looked back. So today, it is my hope that I am going to spark your interest in the field of pharmacometrics, and so that you can go on and apply this concept in your respective research. Or if you're a young graduate, you are looking forward to an area where you are interested. So I hope I will be able to spark your interest today. Now, before I start, I would like to mention that you kindly hold all your questions till the end of the talk, and then I will take all the questions together at once. Also, because this is a personal thing, I get distracted when my camera is on while presenting online. So I am going to switch off my webcam. So thank you for your understanding. Okay. Okay. So today's webinar is, you know, today is the day one, and I'm going to cover the fundamentals of physiologically based pharmacokinetic models, which we refer to as PBPK, as well as population pharmacokinetic modeling, which we refer to as POPPK. Okay, so here is an outline that I am going to be working with today. First, I am going to start with a brief introduction to models and modeling. And after that, I am going to give a generic introduction to population pharmacokinetics as well as physiologically based pharmacokinetic modeling. And finally, I will demonstrate the use case of these approaches in 2 of my previous projects that I have completed. Since, I've been talking, I'm mentioning models. So why not start with, the basics? So what exactly do we mean when we say models? Now, a model is a simplified representation of a real-world system, okay? It can help us to understand, analyze, or even predict how a system works. And, maybe we know that models are everywhere, even sometimes when we are not conscious of it. So in a real-world system, we can have a complex situation, but when you try to model the real world, what we try to do is we want to focus on the most relevant aspects of that system. So by ignoring unnecessary details, okay? Let us look at 3 broad classification of models today. The first class, I would call them physical models. So what do we mean by physical models? Physical models are like tangible, realistic, scaled down versions of a system. Such models are intended to look almost exactly like the system that we are observing, okay? So let's take, for example, a cardboard house, okay? Now, when you make a replica of your house with a cardboard, then you can say that you have built a physical model of your house. The question then is, what can you do with this model? You can try different scenarios. For example, you want to paint your real house. So because you have a model of your house, you can try to apply, painting your model house, see how it looks like. When you're happy with it, then you can apply what you learn from that into your real house, okay? So in this kind of models, we want to make the real world system to be as realistic as possible. So because of that, we don't want to make a lot of assumptions because we want to include as many details as possible, okay? Now, the second type of models that we have are called conceptual models. And here, the models are usually a high-level abstract representation of a system. With such models, we can mentally visualize how different components of the systems are related. For example, look at this organizational chart for a library, okay? This is an abstract way of describing how the library works. So instead of you showing the students around, with this conceptual model, the students by themselves can, understand how each part of the systems are interconnected. Whenever I enter a library, where do I go? Where do I submit my card and things like that? So conceptual models can help you to have that visual or mental understanding of how the process works. Okay, the final type of model that we have are called mathematical models. Now, in mathematical models, we simply use mathematical equations to describe the system. Let us consider this model of inflammation repair process in the body, for example. I know you are probably thinking right now, is this not a conceptual model that is showing how each of the model's components are connected? Okay, so if you think like that, well, maybe you are right, and that means you are following me so far. But what makes the difference is that, in mathematical model, we are interested in quantifying the relationship between each of these components. Okay, for example, if I make this decision instead of this, what impact does that have? How much increase or decrease do we have? So when you start to think about this, then you're already thinking in quantitative terms, and that means you are thinking of mathematical models. So if you look at this figure alone, then we are talking about a conceptual model. But by the time you start describing how different components, inside this conceptual model are related with a mathematical equation, then what you have now described is a mathematical model, okay? Now, before we go on to discuss, models further, let us quickly do a quick refresher in pharmacokinetics. As we all know, pharmacokinetics refers to the processes that describe what the body does to a drug after the drug enters the body. And these processes generally involves absorption, distribution, metabolism, and excretion, which we generally refer to as ADME. Okay. Now, these processes combined together determines drug concentration in our body and tissues at any given time. Okay. Now, let us say that you design an experiment, you conducted an experiment, and then you collected drug concentrations in the blood, okay? Now, data from this kind of study can help us to understand some of the properties of the drug. However, there are several things that we may not be able to directly measure in these patients, either due to ethics or practicality. Let me give you two examples. For example, if you want to know how long does this drug stay in the body, if you want to design an experiment with this question in mind, then that means you have to keep the patients in the hospital for a very long time. So that means you are not being practical with your design. Another question is, let's say you are interested in a drug that works in the brain. And so you are not just interested in what is the concentration of the drug in the blood. You want to know what is the concentration that actually gets to the brain because of the blood-brain barrier, okay? So if you are going to conduct a study where you want to measure drug concentration in the brain of human beings, you probably will not get ethics approval, as we all know, okay? So in these kinds of situations, that is where pharmacokinetic models can come to the rescue. And with pharmacokinetic models, we can answer questions like this and even many more, okay? Now, before I move on to the next slide, I would like to mention that in pharmacokinetic models, the system that we want to represent, are basically these four pharmacokinetic processes, and that's it, okay? So let us now talk more about pharmacokinetic models on the next slide. All pharmacokinetic models are generally described by mathematical equations. So therefore, we can say that pharmacokinetic models are a subset of mathematical models. And broadly speaking, we can put all pharmacokinetic models into three buckets. In the first bucket, we have empirical models. So what do we mean by empirical models? Empirical models are models that are purely data-driven. So what do I mean by purely data-driven? That means if you don't have data from the subject, there's nothing you can do. You can't model anything, okay? So that is, you conduct an experiment, you collected data, concentration data, and the only thing you are interested in is summarizing this data, or perhaps you want to fit a very simple line through the data points in order to estimate important pharmacokinetic parameters like Cmax, Tmax, AUC, and so on and so forth. So because these models are quite simple, we don't integrate, underlying mechanism or physiology of the system into these kinds of model. Well, maybe everything I've been saying since morning is a little bit abstract. So let me put an example to make it clear. For instance, in this basic one compartment IV model, the box you are looking at here, which I labeled compartment 1, it has no physiologic interpretation. For example, if I just draw this box and I put number 1, if you ask someone who doesn't have experience in modeling, they can't really interpret, what you mean in terms of what happens in the body. So that is what we mean by when you are doing empirical model, there is no mechanistic understanding to the layout that you have for the model, okay? So our goal as pharmacokinetic modelers is just to estimate these important PK parameters that describe, processes of absorption, distribution, metabolism, and elimination that I mentioned earlier. For example, absorption, you are looking at Ka. For example, distribution, you are looking at volume of distribution or even clearance, okay? All right. Now, the second bucket, we are going to call those kind of models semi-mechanistic models. Now, these models are primarily mechanistic in nature. They are partially mechanistic, I beg your pardon. So some of the components have some physiologic interpretation. For example, let us say that you are modeling a drug that is given by mouth, that is orally. It is going to take some time before the drug appears in the blood, okay? So you can reflect this understanding in your model. And here is an example of what I'm saying. So you can imagine compartment 1 as your gut, and then compartment 2 as the blood, where you are collecting your drug concentrations. So the drug has to first go into compartment 1, and then when the drug gets into compartment 1, it takes some time, or the drug experiences some delay before the drug appears in compartment 2, which is the blood. So as you can see, we start to put some realistic representation of what is going on in the body into our model. So because of this, we say that semi-mechanistic models are a little bit complex compared to empirical models, okay? And because of this, we can use it to describe several processes going on in the body. Now, finally, I want to talk about the third models, which are called fully mechanistic models. Now, these models try to describe biological and physiological processes in great details and in a realistic manner. That is why we call them mechanistic models. So in this type of models, every compartment, that is all these rectangular boxes that I have shown on the slide, so each of those compartments that you are going to put in your model represent, something that is realistic about the system, about the human being, okay? And parameters in the model must also have some physiologic interpretation. For example, let us look at this model. In this model, you can see that we have several compartments, that is the rectangular boxes. But when you look at each of the rectangular boxes, we label them according to what happens in the human body. So take the compartment depicting the heart, for example. We describe it using the true value of human weight, the true value of human blood flow. So everything we are using to describe the model are those things that are true about the human being. So because of this, these kind of models require the greatest number of details, and they are the most complex out of these three models that I have described so far. Okay, so the first two models, we can use it in population pharmacokinetics, while the last model, we use it in building physiologically based pharmacokinetic models. So to summarize, let us look at the comparison among these three models. So fully mechanistic models are the most complex, as we have seen, okay? The compartments in empirical or semi-mechanistic models, they have no physiologic interpretation, okay? Now, you need data from subjects to develop and fit, the models when you are dealing with empirical or semi-mechanistic models. Why in fully mechanistic models, you don't really need to have a data. So because of this, we refer to empirical and semi-mechanistic models as top-down approach, while PBPK models are referred to as bottom-up approach, okay? Then variability can be captured in both mechanistic models, okay? And here are some examples of models in each class. For empirical models, we have NCA, we have POP-PK, very simple population pharmacokinetic model. And then for semi-mechanistic models, we have some POP-PK models where you put some mechanism into the models, like target-mediated drug disposition and things like that, or indirect response. And then we have examples of fully mechanistic models like PBPK or QSP, all right? So for my own part of this webinar series, I am going to handle the fully mechanistic part, which will, and I'm going to demonstrate this with physiologically based pharmacokinetic modeling. Now, having said that, my goal in today's webinar is to get everyone comfortable with both approach at a very high level. And then in subsequent webinars, we can go into more details about each of them. Now, let us consider the dynamics of a simple one-compartment model. Imagine that we simplify the human body into this one-compartment model, represented by this box X. If you drink a bottle of Coke, the Coke goes into your blood, but after a while, we know that the Coke has to leave the body, okay? So let us represent how the Coke enters the body and leaves the body with these two arrows. Now, up to now, what we have done is that we have described a simple conceptual model of how a drug moves in and out of the human body in a very simple way. And that is the whole essence of empirical model. I want to simplify the model as best as possible. Now, if you want to know how much of the Coke remains in your body after 2 hours, for example, then you are going to need to describe what is happening in the body with ordinary differential equations to answer such questions. So for example, let us say after you take the coke gets eliminated or gets out of the body at a rate constant called Kx. Then we can write a mathematical equation to represent the model like this. Now, basically, this equation describes the amount of coke in the body. When I say body now, I'm referring to compartment X. So it refers to the amount of coke in compartment X or the body over time. In this equation, X initial represents the dose that you put into the body, which is the dose of the coke or all the coke that you took. And our output is the gradual loss or elimination of the coke out of the body. And we have said this is at a rate constant of Kx. So if you put all this together, you can see that we have described what is going on in the body. And let me mention that the negative behind the Kx, is what signifies loss of the coke from the body, okay? I'm going to ask if we are following so far, so that I don't, before I put more complexity on what I have described so far. So is it good so far for all of us? Or at least majority?
Yes, I think you can continue.
Okay. All right, so now let us say that we want to be more realistic about how the body works. And then we want to reflect this in our model, okay? We know that when we take a drug by mouth, all of it first go into the stomach. And then as time goes on, some of the drug enters the system, that is the blood. Now, we can represent this model like this. Okay. So we can represent this model as I have shown on the slide. So you see, now we are trying to be more realistic or mechanistic than what we have described in the first scenario. So assuming that you give a dose of a drug, okay? Now we represent the rates in the model as Kg, Ke, and Kb. So we can now think of these dynamics as input and output for each of the compartments. So the direction of the arrow can guide us to know what constitutes an output and what constitutes an input. For example, let us focus our eyes on the gut compartment for a moment. So in the gut compartment, what is the arrow coming in? That is the input. What is the arrow going out? That is the output. So the arrow coming into the gut compartment would be the dose. So that is the input. While the arrow going out of the gut compartment is both Kg as well as Ke, and those would be our output. So if we also focus our eyes on the blood compartment for a moment, then we can say that the input for the blood is Kg dictating the loss from gut into the blood, while output for the blood compartment is going to be the Kb, which is determining what goes out from the blood. Okay, now with this in mind, we can write mathematical equations to describe these input and output processes for each of the compartments and link them together as shown in these equations. Okay, so let us now do a simple mental exercise together. And
can you please go slowly a little bit? Can you go slowly? There is
okay.
From the show that you are too fast.
Oh, okay. Yeah, I'm trying to also race against the time, but okay, I'm going to try my best to go slowly. Okay, so what I am saying is that if we look at this compartment and we focus on the gut compartment, let's look at the gut, the rectangular gut compartment, okay? Now, if I ask you what are the inputs, what are the outputs for that compartment? Input simply means what is coming into that compartment. Output means what is going out of the compartment. So the input in this case would be the dose for the gut, because we are looking at the gut right now. So I don't want you to look anywhere else, just look at the gut. So the input is the dose, that's the arrow coming in. The output is the Kg and the Ke, okay? Now, let's now focus to the blood. Now, if you focus your attention on the blood compartment, the input for the blood compartment is the kg, that is the arrow coming in from gut into the blood. And then the output for the blood compartment is the arrow coming out of the blood, to outside the body or wherever. Now, with this understanding of input and output processes, we can write mathematical equations to describe these input and output processes for each of the compartments and link them together as I have shown on the slide. Okay? Let us now do a simple mental exercise together. And I am going to ask you a question afterwards. I hope, it is my hope that you follow. Okay? Now, if we add another compartment to represent the organs within the body, okay? And we want to describe the dynamics again. How many inputs and how many output do you think we have for the blood compartments now? Well, let me answer this first one, and then I can ask you the second one and you can respond. So if the question is, I want to know what are the inputs, what are the output for the gut compartments now. So if you focus your attention only on the blood compartment, then you can see that we have arrow kg, one coming from the gut into the blood, and then we also have an arrow dictated by K star, that is drug leaving the blood and going into the organ. So those are the two outputs that we have. And then what would be the two inputs into the blood compartment? What are the two arrows coming into the blood compartment? So, the arrows, two arrows coming into the gut compartment will be the kg and then the K star from organ into the blood. The arrows going out of the blood compartment will be the KB as well as the K star going from blood to the organ. Okay, so my question then is, how are you going to write a differential equation or a simple equation to describe what goes on within the blood compartment? So now that we understand input is from gut and another input from organ, output is something going from the blood to the organ and something going from blood out of the body. So if I ask you which of these equations will represent what is going on within the blood compartment? So I'll pause for a minute and see if anyone answers, then if not, I would move on. Okay, I mean, if you want to respond to any question, you can simply put it in the chat because of time, we may not be able to have an interactive session at this time. So interactive session may come at subsequent webinars, but right now, my goal is to describe the concepts, okay? So if you picked C, then you are correct, okay? Now, let us briefly talk about population pharmacokinetics. The popular acronym in the field for population pharmacokinetics is POPPK. So when I say POPPK, I am referring to population pharmacokinetics, okay? Now, let us say that you are conducting a pharmacokinetic experiment on a single subject, and then you measure blood concentrations over time, okay? So once your result for the blood concentration comes from the lab, then you plotted this concentration against time for that subject. Now, the question then is, what do we do with this data? Well, what we can do with this data is we can connect each of those data points, and our goal is so that we can calculate important PK parameters like Cmax, Tmax, clearance, AUC, and what have you. Now, there are two ways we can obtain these PK parameters, two ways. The first method is what we call a non-compartmental analysis approach. And what do we mean by non-compartmental analysis? It simply means I am using some kind of algebraic equation, to calculate these parameters, okay? So when you use this approach, you can use it to calculate things like, Cmax, You can use it for AUC. If you remember very well in pharmacokinetics, we use, this trapezoidal rule to calculate AUC, or you can, look at Tmax from the graph. So when what you are doing is nothing but this, then that means you are not making any assumption, you are not making any compartmental models. So you are basically using some equations that have been established to calculate your pharmacokinetic parameters. So when this is what you are doing, then that is when we say that you are only doing non-compartmental analysis, okay? Now, another method for us to calculate some of the parameters is called compartmental model approach. And in this approach, our goal is to estimate important PK parameters, like clearance, absorption rate constant, Ka, or intercompartmental clearance, Q, or even volume of distribution, which I refer to as VC on the slide. Now, both models have their advantages and disadvantages. For example, non-compartmental analysis, which I refer to as NCA, is performed on the raw data that you collected from the clinic. So therefore, I can tell you for free that FDA, as an organization, or regulatory authority, they are going to, if you tell me AUC result from doing non-compartmental analysis and your study was well designed and you have a very rich samples, then I am going to believe your NCA results because you are doing the calculation from the observed data. You are not using any model, you are not using any assumption. So regulatory authorities can believe whatever result comes from that kind of analysis. And that is why whenever we want to demonstrate bioequivalence, the regulatory authorities will ask us to show the bioequivalence on important NCA parameters like Cmax or AUC, because they want to see what is happening exactly in the subject, okay? Now, the problem with this is that for you to be able to do this, you must have collected a very rich data in the subject. That is, you collected concentrations every 1 hour or every 2 hours, or, the best way you can design the experiment. And you and I know that this may not be realistic in all situations when you are conducting clinical trials. The second problem with NCA is that you cannot use it to calculate some pharmacokinetic parameters. For example, you cannot obtain like intercompartmental clearance Q from NCA analysis. You cannot obtain absorption rate constant, for example, or even clearance. Although there are some formulas we can use to approximate them, but these are going to be, kind of off or inflated. So if you want to get them realistically, then you can use compartmental approach, okay? Another advantage is that, another disadvantage of NCA is that, if you are in a drug development process and you are in phase 3, you probably will not collect rich data from subjects. So that is why NCA approach might not really cut it when you are dealing with this kind of data. Now, let us come back to reality. Let's come back to reality, because everything I've described so far is just one subject. So, but we know that whenever we do an experiment, we use more than one subject, okay? So, in these studies, where you use more than one subject, there is going to be differences from one subject to another subject. So that means that there's going to be some kind of diversity with respect to weight, with respect to age, gender, or even disease status and what have you, okay? So the data from this kind of studies would look something like this, okay? Now, when we model, this kind of data using compartmental analysis, then the parameters that you have calculated, we are going to call them population parameter, because the previous one I described, I am only talking about one subject. So that's why I call those model parameters individual parameters. So the clearance will be individual clearance, individual volume, individual K. But in the real world scenario where you use more than one subject, then your model is going to estimate, population parameters. That is, the clearance will be the clearance for the population, the volume will be the volume for the population, the Ka will be the, absorption rate constant for the population. Now, because of this, we are using more than one subject. So there's going to be some kind of variability, within your result. And we know that, for example, if you do this kind of experiment, the clearance you get for individual 1 might be different from the clearance you get from individual 2, might be different from the clearance you get from individual 3. But when you estimate it in your model is giving you one single clearance value that represents the whole population. So then you can now, in addition, also describe, the spread of that clearance, which is what we call, variability. Okay. So on the next slide, let us look at variability, further. Now, when we say variability, for simplicity, I'm going to use fewer number of subjects to explain. I am sure you would agree with me that the result from one subject to another subject is not going to be the same. So variability is called between subject variability when you observe differences from one subject to another, okay? And I can assure you that if you conduct an experiment, especially human experiment, there's always going to be between subject variability, because it is not possible that you do an experiment in 2 subjects and you get exactly the same value. So there's going to be some variability from one subject to another. Now, this variability is represented as eta in the model, and we generally call it BSV, between subject variability, okay? Now, the question you probably have in mind now is that, what could be the potential sources of this variability? What can make the result from one subject to be different from another subject? If I ask you, all of us can, mention several potential reasons that can cause this. For example, there might be differences in age, there might be differences in weight, there might be differences in gender, and so on and so forth, okay? Now, we can put these factors and group them into 2. One is intrinsic factors, another one is extrinsic factors. Now, what do I mean by intrinsic factors? Intrinsic factors are factors that they are beyond the control of the subject or the patient, okay? For example, if you are a female or you are a male, you cannot control your gender. You cannot say, I am male today, biologically speaking though. So you can say, I'm a male today, then for the purpose of this study, I want to be a biological female. So this is not realistic. So intrinsic properties are those properties or factors that it is beyond the control of the patient, it's just there, okay? On the other hand, we also have extrinsic properties. Extrinsic properties are properties that the patient can still control it. For example, co-medication. A patient can control it by, okay, I'm not going to use this drug now. I will use it after 2 hours. So you see, they can control that. Or smoking status. So, okay, before I use this drug, I'm not going to smoke, or I won't smoke for 2 days. So these are things that the patients can control. Okay, so both intrinsic and extrinsic factors are referred to as prognostic factors. And in POP-PK, the simple word we refer to it is, we simply call them covariates. Okay, so in population pharmacokinetics, we say that between subject variability could be explained by the different covariates that we have in the population. So that is our goal. We observe between subject variability. Now we want to explain what is the source of this variability. So we can use these different factors to understand what is causing the differences, okay? Now, another source of variability is what we call within subject variability, within subject variability. Basically, what we are saying here is that if you do an experiment today and you determine drug concentration in subject after 5 hours, if you repeat the same experiment in the same subject tomorrow, it is possible that, the 2 results you are going to have might not be the same. It's very possible, okay? So in this case, the driving factor for within subject variability, we can categorize it into 2, and I will explain, okay? So the first one, we can say it is between occasion variability. Now, what do I mean by between occasion variability? Let's say, for example, on the first day, the patient took the drug on an empty stomach. Now, you repeated the experiment the following day, but the patient ate before taking the drug. So if you observe any differences between the same subject today and tomorrow, we could actually attribute the differences to, probably it could be because of the food that was present in their stomach when they did the study today. So as you can see, this is what we call food effect, okay? So, and that is why we call it between occasion variability. So in occasion 1, we use a different condition. When the same subject came back again, we use another condition. So that's why we call it between occasion. So each of these things are called occasion, okay? In fact, if you give a dose to a subject today and you give the same dose to the subject tomorrow, there can also be differences. So that is what we call between dosing variability, which still falls under between occasion variability. So every dosing for each of the patients can be regarded as occasion. So this is what we mean by between occasion variability. And this is, excuse me. Okay, so this is, we regard to this as BOV, and the notation we use for it in population pharmacokinetics is kappa, okay? Now, the second type of variability that we can have, we are going to call it random unexplained variability. And these are variability that you just cannot explain. You don't know what is responsible. And I'll give you an example. Some of us who are, who conduct experiments every day with HPLC, we know that if you run the same sample through an HPLC machine, the same sample, you run one now, and then after that one finish, the same sample, you run it the second time, it is possible that you don't get the same result. So how will you know what is causing these differences? You probably would not know. It's just going to be a guesswork. Could it be the flow rate? Could it be the temperature? You probably don't know, okay? So this kind of errors, we call them random unexplained variability. And we generally refer to them as errors in general, okay? So, and we can simply say this kind of error is as a result of measurement. That's measurement error. So there are also other examples of random unexplained variability, like model misspecifications, that is using a wrong model for a drug, okay? So this variability can be referred to as RUV, and we generally represent it in the model as epsilon. Now, please note, let me say this, that I am trying my best to be general, okay? Because this is an overview. There are more nuances and distributional assumption that goes with these variabilities, and I'm sure that maybe when you are taking the population pharmacokinetics series, we are going to talk more about this. Now, in population pharmacokinetics, our goal is to estimate the pharmacokinetic parameters of a drug at the population level. For example, parameters like Ka, clearance, Q, and those things I mentioned on the slide. Let us now think in simple statistics for a moment. If you collect the weight data from 50 subjects, simple statistics, we would summarize the results using average and standard deviation. So that means you are describing the mean of the weights, and then you are trying to describe the spread of variability, of this weight across the 50 subjects. So that's why we are using the average and the standard deviation, the mean and the spread of the data. You see, it is exactly the same thing that we are doing in population pharmacokinetics. I can tell you that for sure, okay? The only difference, I repeat, the only difference is that we don't directly measure the pharmacokinetic properties. For example, when you do your study and your patients come to the clinic and you want to collect data from them, you don't collect clearance data from the subject. You don't collect, Ka from them. What you collect is concentrations. Now, we need a sophisticated model, a sophisticated software to convert these concentrations that we have collected into, these parameters like clearance, Q, Ka, and things like that from those concentration data. So it is because of this that we can use any simple statistical software in population pharmacokinetics, because what you are having from the subject is concentration. The population parameters that you want to describe are not concentration per se. They are these pharmacokinetic parameters which you did not directly observe, So you need a sophisticated software to help you to convert this concentration to these parameters, and then you can do your population analysis, okay? Now, these are the parameters that we generally want to calculate, and they are referred to as theta, okay? In population PK, we refer to those parameters as theta. For example, if we are talking about Ka, the Ka for the population will be theta Ka. For clearance is going to be theta CL, and so on and so forth, okay? Now, let us look at different approaches that we use in population pharmacokinetics to estimate this theta, okay? Now, there are 4 different approaches that we have so far, and I will explain each of them as best as I can. The first one is called the naive average analysis. And let me explain this using an hypothetical result from a study. So let us say that you conducted an experiment where n is equal to 5. And here are the concentrations you got at 4 different time points. In a naive average approach, what we want to do is to simply average each of these concentrations for each of the times, okay? And then, so for example, at 1 hour, I want to average all this concentration and then get a value. At 3 hours, do the same. At 6 hours, do the same. At 9 hours, average all the concentration, because all of them, we took them at the same time. So what you are going to get is something like this, all right? So in naive average analysis, what you are doing is you simply want to fit a model to all those averages. You want to fit a model to all those averages. And if you remember, we started from 5, but now we only have 1 data, average data. So when you fit the model, there's only 1 parameter you can get. That is the parameter for the population, because we have taken all the individual values and converted them to average. So the only value you can get from here is population. So my point is that whenever you are doing naive average analysis, the best you can get is the population parameter, okay? Now, let us think what happens in clinical scenario in realistic manner, okay? You would realize that it is practically impossible for you to obtain samples at exactly the same time as I have shown on this slide, okay? And where I'm getting at is that this kind of data, you know, before you can get it, you have to do the experiment in a very strict control manner. And you and I know that if you want to do experiments in human beings and you want to strictly control all these things, it is practically going to be impossible. The only time you can have this is when you are working with animals, because when you are working with animals, you have control over when you are going to collect the samples. So that is the only time you can have this kind of data. And because of that, naive average approach is usually used for animal data, animal experiments, okay? Now, in a more realistic way, what you would expect when you conduct studies in human being is going to look like this. For example, I plan to collect samples at 1 hour, 3 hours, 6 hours, and so on. But some of the patients might come 20 minutes late. Some of them might come, 10 minutes earlier. So you are not going to have the concentrations at exactly the same time, okay? So because you don't have this concentration at exactly the same time, it is going to be difficult for us to use the naive average that I explained earlier, because these concentrations are not obtained at exactly the same time point. Therefore, I'm going to talk about the next approach, which is called the naive pooled approach, okay? Now, in this naive pooled approach, if you look at this study, we have 5 subjects. Let us imagine that these subjects are subject green, subject yellow, subject purple, and so on and so forth. So what we do in naive pooled analysis is that I am going to pool all this together, all this data together, and I am going to assume that this data come from just one big subject, okay? I'm going to put all these concentrations together and assume they come from just one person. Then, when you assume all of these concentrations come from one person, you are going to fit the data, and then you get your population estimate or population parameters, okay? So with this approach also, the best you can get from the approach is the population parameters. You get the population parameters clearly, but you will not be able to describe the differences between one subject to another because, again, remember the assumption, we assume all these concentrations come from just one person, although we had 5 subjects. So that is the limitation of naive pooled analysis, okay? Now, the next approach that we use, that's the third one I'm talking about, is called two-stage analysis. Now, in two-stage analysis, as the name implies, the analysis is done in 2 stages. In the first stage, what we do is that we are going to fit the data of each of the subject first. I fit for green, I fit for yellow, I fit for each of them, okay? Then after fitting for each of them, I'm going to obtain the parameters for each of these subjects one by one. So I'm going to get clearance for the blue subject. I'm going to get clearance for the purple subject. I'm going to get clearance for the green subject. And then once you have all this, we say that we have estimated the individual theta. You are not estimating the population. You are estimating the individual parameters, individual theta, okay? Now, in the second stage, then we can now fit an average line through each of the data to obtain the population estimates. So when you now bring all this data together and then you estimate the population parameter, so that is when you are now doing the population pharmacokinetics. And the beauty with this approach is that because I already have individual value for the theta, now I am obtaining the population parameter, which is the mean, then I can describe variability. I can describe how does the value for this subject green differ from this subject yellow, differ from this subject green, and how do they differ from the population parameter. So you can see that we can now describe, variability, so to speak. But the problem with this approach is that because you want to fit the data for each of the subjects one by one, then you must have, or the requirement is that each of the subjects must have enough data points for you to be able to calculate the parameters. Maybe that is too much verbiage that I'm saying. What I'm saying is that let us imagine that subject green only has 1 concentration collected. If subject green has only 1 concentration collected, then it is going to be very difficult for you to obtain the individual theta, the theta I for subject green. So that is why I said this method is only good when you have rich data for each of the subjects. Then you can use this approach, okay? Now, the last method, which is the most popular method by far, is called one-stage analysis, okay? Now, in one-stage analysis, we are going to, start by fitting an average line through each of the population to obtain population parameter like this. So because I am fitting all the data together, I am going to get at that first stage the population parameter, and I am going to be able to describe the variability in the population. So the parameters that relates to pharmacokinetics are called fixed effects, and then those parameters describing your variability are called random effects, okay? Now, in this first step, again, the data from the subjects are combined and modeled so that we can estimate the population mean and their variability. So the typical mean population parameters are referred to as fixed effects, while the variability of the parameter are referred to as random effects. I've explained these parameters earlier on, so I don't want to, keep repeating that. Now, what do you then do? The next thing we do at the second step is that we are going to use the results from the first stage, to then refine and estimate what is going to be the value for each of the individual subjects that we have, all right? So that is why this is called the post hoc step. So in one-stage analysis, you first do your fitting all the subjects together, and then the post hoc step, you then use the results from the population value, the fixed effect and random effect to estimate what is going on in each of the individuals, okay? this is like a high level. I mean, we can talk more about the nuances involved in the approach, but this is just a very high level of what is going on in one-stage analysis, okay? Now, one-stage analysis has advantage because it can help us to estimate both the population and the variance reliably, okay? You don't need, I repeat, you don't need to have rich data in each of the subjects before one-stage analysis can work. And that is why the most common method that they use in analysis in softwares like NumMem or Phoenix or Monolith that we use in population pharmacokinetics, all of them use this one stage in their estimation. So this one-stage approach is generally referred to as nonlinear mixed effects. Now, what do we mean by mixed effect? Mixed effect because you have two types of effects. Number one, you have the fixed effects, which are the typical population parameters. And then you have the random effects, which are describing variability between each of these parameters, okay? All right, now let me quickly just give you, if I have a population pharmacokinetic project, how do I go about it? So this is going to be a high-level process that we follow in any population project, but this is going to reflect some of my own personal philosophy. First, I am going to start with what is the questions that I want to ask with this analysis. The next thing I'm going to do is I'm going to then collect data. Since I know the question I have in mind, I'm going to plan to collect data. Now, where do you get your data from? Where you get your data from is going to depend on either you conducted the experiment yourself and you want to analyze your data yourself, or even maybe your collaborator conducted an experiment and then they gave you the data for you to help them analyze. The second source of data could be from a pharmaceutical company who is developing a drug to be approved by the FDA. So when they do the clinical trial, they can give you the result as a modeler to help them understand what is going on with their drug, okay? Now, I quickly want to mention, I'm a little bit digressing here, that I understand that, in Africa, we generate a lot of data from clinical research, but I don't think we analyze this data extensively. Okay, I understand this may be due to the lack of skills, that, people that have this skill, they are not a lot in Africa for now. Even especially in Nigeria, I'm sure not a lot of people are familiar with this approach. So, and that is one thing that this webinar is aiming to, one of the goals of this webinar is to expose people to this approach so that, we can start thinking of collaborating with each other. Where someone has the skill, you can analyze the data for somebody who doesn't have it. And then we can see much more improvement and much more results coming from Africa in terms of understanding these drugs. Because trust me, if you pick a drug today and you look at the clinical development packet, you would see that most of the subjects in whom the drug was developed or tested are going to be, majority of them are going to be people, outside of Africa. And probably, I don't know, maybe it's because, we don't analyze our data and put all these results out there. Okay, now that I have the data, the first thing I am going to do is to understand the data by performing various exploratory analyses. For example, I'm going to check the data whether there's no outlier. For example, you collected data and some of the subjects are weighing 700 kilograms. You and I know that 700 kilograms might be unrealistic. So maybe the person who is handling the data input mistakenly put 700 instead of 70. So that is why you want to check the data to make sure that whatever you are putting into the model, they are realistic estimates, that you are putting into it. And then you do univariate analysis. For example, you plot histogram of each of the covariates, or you do a scatter plot, or you do multivariate analysis. Basically, you correlate. You want to say, does weight correlate with age, or does this variable correlate with another variable? So all those information can help you to decide how you are going to approach the model later. Then the next step you are going to do is to model the data. And when I say model the data, you are going to start by developing structural model for the data. Then you include variability. Once you are happy with that, then you include, covariates, and then you assess correlation. Now, one thing I must say here is that for example, if you want to decide between which structural model should I use, so it's either you use 1 compartment, 2 compartments, or 3 compartments. The question now is, how do you decide whether you are going with 1 compartment or you want to go with 2 compartments or 3 compartments? So that is where we use statistical criteria to identify which model is going to be the best. And some of these criteria include objective function value, which we call OFV, or Akaike information criterion, which we call AIC, and many others, in order to identify which model is the best, okay? So usually on the slide, 1 and 2, we usually do it side by side, all right? Now, once you are happy with the model, the next thing is then to evaluate whether my model that I have now can estimate population parameters reliably, okay? So what I mean is that if I run this model again and again, am I going to get the same result, okay? So you are trying to see what is the level of parameter uncertainty, or, what is the robustness of my parameter in terms of, doing bootstrap analysis. Finally, what we then do is that we simulate different scenarios with the model that we have, okay? So that, in a way, concludes, introduction to population pharmacokinetics, how we approach the modeling processes. And then at the subsequent webinar in future, we are going to look at each of these processes in more details. Okay, so let me now switch over to physiologically based pharmacokinetic models. Now, again, I am going to talk about physiologically based pharmacokinetic models at a very high level. And, subsequent webinar, we can go into the nitty-gritty. In physiologically based pharmacokinetic models, we try our best to represent the human body as close as possible, okay? What this means is that we want to structure our model to represent all the important organs involved in important PK processes in the body. Basically, we want to describe absorption, distribution, metabolism, and excretion, okay? Now, we use different compartments to represent each of the organs in the body as shown on this slide. That is why PBPK models are referred to as mechanistic multi-compartmental models. And on the slide, the red and blue arrow that you are seeing depicts the way human fluid flow within the body. And when I say human fluid, the most common one that we use is the blood flow or the blood circulation, because that is what essentially distributes the drug around the body, okay? Now, let me quickly mention that we can develop a PBPK model to represent any biological system that we are interested in, analyzing or observing. For instance, we can create a PBPK model for a human being. We can create a PBPK model for a mouse, for fish, for dog, and so on and so forth. All you have to do is to simply change the system parameters to match that of the species you are interested in. I'll talk more about this later. So because of this, PBPK models have great flexibilities, and therefore they have several applications where data is lacking. For example, in most experiments that we do in our clinics, we generally collect samples from the blood of the patient so that we can measure drug concentration. However, it is challenging to measure drug concentration in other parts of the body, for example, the brain, cerebrospinal fluid, or even the lymph. So in these kind of situations, we can use physiologically based pharmacokinetic model to predict drug behavior in these anatomically hidden compartments, okay? In addition to this, we can also use PBPK to build different physiological conditions, such as, we can adjust the model parameters to build a younger adult or a younger human being, that is pediatrics. We can build a model for pregnant women. We can build a model for somebody that is lactating, okay? Now, let me describe the PBPK model development parameters that we use whenever we want to build the model. So there are two parts to any PBPK modeling exercise. The first thing you want to do is that you want to build a human being on your computer, okay? I use that word literally. Now, what that means is that I want to create a virtual human being on my computer, okay? Now, the second thing then you want to do is that you want to integrate the properties of the drug that describe absorption, distribution, metabolism, and elimination. So these properties of the drug, you want to incorporate it into the model. For example, parameters like log P, which determines absorption or effective permeability, or parameters that describe distribution like fraction unbound and so on, or parameters that describe metabolism and elimination, such as intrinsic clearance, okay? Now, why are we building this model? The reason why we are building the virtual human model is to be able to administer a drug to the model. So that is why this step is very crucial, and we always do it every time for a new drug, okay? So what I mean by this is that if I build a virtual human setup, the virtual human setup does not have to change all the time. The only thing that you are going to change is going to be, if I want to test, let's say, paracetamol, for example, you put properties of paracetamol and then you simulate. If I then want to change the drug, I want to now test for, let me think, maybe aspirin, for example, then you change the drug-specific parameters from that of paracetamol to that of aspirin. So the virtual human model itself remains constant. The only time where your virtual human model can change is if you are changing from one setup to another. For example, I have a model for adult human male. Now I want to build a model for a pregnant woman. Then that means these two systems are completely different. So that is when you need to now have a new virtual human setup for a pregnant woman, which is going to be different from that of an adult male, okay? So I will talk about each of these setup in the next workshop. Now let's talk about model development workflow for PBPK models. Now you are going to start with, setting up the system with different parameters that describe anatomy, physiology of the system, for example, organ weight, blood flow, and so on and so forth. And on top of that, you are going to set up parameters that describe ADME properties of the drug, as I have mentioned on the previous slide. Now, when you bring these two together, you now have a PBPK model of the drug. So the next question is, how do I convince people, or how do I convince myself that this PBPK model that I have built for this drug is reliable, okay? So to demonstrate that the model you have built is reliable, then what we do is that you simulate with the model, and then you are going to compare the results from your model to what has been reported before. So if your model needs adjustment, then you go back to some of the parameters and then you adjust it and see whether your model improves, okay? Now, once the model improves and you are happy with the results and the model result aligns with the observed data, what you then do is that you say, okay, my model is now validated, all right? So once your model is validated, what do we do with it? What we do with it is then to, simulate or perform simulations for different scenarios in order to answer the research questions that you have in mind, all right? So this is a broad overview of how model development workflow in PBPK model development works. I'm going to talk in details more about this at subsequent webinars, okay? Now, let us talk about applications of pharmacokinetic models. There are two broad areas where modeling and simulations with pharmacokinetic models are useful, okay? The first area I want to talk about is in the area of drug development, okay? I'm sure many of us are aware there are different phases of research before a drug gets to the market. Now, models are used in different aspects of this drug development stages, okay? For example, we can use physiologically based pharmacokinetic models to guide us to know, okay, this done in animals at preclinical stage, and then take those parameters, put it in the model, and then, to use it to develop a PBPK model, and then get some predictions for what the concentration is going to look like in human being. Another place where we can use PBPK model is, for example, I can tell you this, that experiment or clinical trials is very expensive, okay? For example, the cost of adding one subject to your trial might run into hundreds of thousands of dollars, okay? So if you have to do a clinical trial, that is why pharmaceutical companies, they sit down, count the cost, look at different approaches that they can use. So this is where PBPK can come in. If your drug compound meets some certain criteria, which is called BCS classifications, then you can approach the FDA that, look, because of this condition of my drug, I can use physiologically based pharmacokinetic model to demonstrate that food does not have impact on my drug, or whether food has impact on it. So instead of doing the clinical trial itself, which costs a lot of money, which costs a lot of time, then you can use your PBPK model to do this simulation and then ask the FDA to waive this study for you, okay? So another place where we can use it is in drug-drug interactions. We can also use it in post-marketing surveillance, all right? Now, for population pharmacokinetics, with regards to drug development, it is widely used across both phase 1, phase 2, phase 3, phase 4, okay? Now, the primary use of population pharmacokinetics, in my opinion, is to help you to enrich your registration trial. And when I say registration trial, this is the trial that when you show the result to the FDA, then the FDA decide whether to approve the drug or not to approve the drug, okay? Now, one of the conditions of the FDA is that whatever dose you use in phase 3, that is the phase where we do the registration trial, whatever dose you test at that place, that is the dose you must market when we give you approval. So that is why, as a pharmaceutical company, the pharmaceutical company, when they want to get the correct dose at phase 2, that they want to move to phase 3. So, and for you to get this correct dose that is not only going to be safe, it's going to be efficacious, then it requires a lot of thinking, a lot of consultations, a lot of modeling and simulations, so that you don't start a trial and then go back to the FDA, oh, we are sorry, we want to change the dose. This is the dose that we think is going to work now. It doesn't work that way, okay? Now, because of all these things that I have said, that is why pharmacokinetic modelers are like gold mines, when it comes to pharmaceutical companies. It's like, I would say that we are like hotcake, so to speak, because, as I have explained, if you are very good in modeling and simulation, then you can help a company to cut their costs. So instead of doing the trial in human beings, costing you millions of dollars, we can use this approach and things like that, okay? So let us now talk about the second area of application, which is in clinical practice and research. There are several applications of pharmacokinetic models on both bedside, that is in the clinic, or in our labs, okay? One area that I can talk about is designing clinical studies. So if you want to do an experiment or you want to do a clinical trial for your research, one of the things that we always plan is, you are going to have a protocol. You need to state upfront what are the times that you are going to collect samples and things like that. So pharmacokinetic modeling can help you to decide on, okay, I need to collect at least 2 samples absorption phase, 3 samples at post-absorption phase. So you can design your study, with pharmacokinetic model in mind, so that it can help you to know what are the best time points that you can collect your samples so that you can adequately describe the pharmacokinetics of the drug. Another use case is in therapy optimization. For example, in critically ill patients or elderly patients, they may show a different pharmacokinetics for a drug. And what I mean by that is this. When you are doing your phase 3 trial to approve the drug with the FDA, you are probably not going to recruit all possible patients. Some of them might be, for example, whenever we are doing phase 3, we don't include pregnant women, okay? So if a pregnant woman, after the drug is approved, need to use the drug by the judgment of a physician, then they need some kind of information to tell them, okay, even though this drug was not tested in human pregnant women, how can we be sure that if I give it to a pregnant woman, the concentration of the drug is not going to go too high or is not going to go too low? Okay, so that is why we can use modeling and simulation to answer, this kind of critical question. Time for questions. Now, in the first project, you see, there is something that we call thromboembolism. And what this means is that excessive blood clotting. So when this happens, we manage it with a drug that is called enoxaparin, okay? Now, in the case of burn injury, clot formation is one of the leading causes of death. So therefore, one of the primary or first line treatments in burn patients is that whenever burn patients come to the hospital, the first thing we have in mind is to give them enoxaparin so that we can prevent clotting of blood. Now, what is the problem? The problem is that the pharmacokinetics of drug generally change in burn patients. And this is due to, what has happened to their body in terms of, damage to the blood vessels, the inhalational damage to their lung and things like that. So if you look at this chart, for example, all these changes occur in a burn patient, which ends up affecting the pharmacokinetics of drugs in general, including enoxaparin. So generally, burn patients would experience, lower exposure to enoxaparin as a result of increased or augmented clearance. So the lower exposure, this is what we have seen, the lower exposure pushes as much as 40% of them outside the therapeutic concentration. So therefore, my goal in this project was that I wanted to characterize what is the factor responsible for this concentration going below the target. And secondly, if we are to give a new dose, what will be the best dose that can push some of these patients within the target concentration? So how did I answer this question? I started by collecting data, okay? So I got data from electronic medical records of burn patients, and here is how the inclusion-exclusion criteria looks like. The next thing I did was that, I explored different approach that I described earlier, exploratory analysis, and things like that. Then I developed a PK model to fit the data, and then I qualified the data appropriately as shown in this chart. Now, what I found was that body weight and total burn surface area were important factors or covariates that are making this concentration to go down in this burn population. So the next thing I did was I then simulated different types of doses so that I can know what is the proportion of patients that are within target if I increase the dose, if I decrease the dose, and things like that. So based on these several simulations, I came up with a dosing algorithm that can be used in burn patients. So you can see this is one of the very beautiful use cases of population pharmacokinetics. And the second case I want to describe here is it's for a condition that is called opioid use disorder. Now, in opioid use disorder, the current standard of care is if you are suffering from opioid use disorder, they give you buprenorphine or methadone in general population. Now, the problem is that these drugs have abuse potential. And if a woman who is using it becomes pregnant, this drug can cause neonatal withdrawal syndrome, okay? Now, on the other hand, there is another drug which is called naltrexone. And this drug is also used for opioid use disorder. And this drug does not have all these disadvantages with the other one I mentioned earlier, okay? Not only that, naltrexone comes in long-acting injectable formulation, which can be conveniently administered on a once-monthly basis, unlike the other ones that are used every day. Now, despite these many advantages of naltrexone, doctors, pharmacists, nurses, clinicians in general, they are still not sure. They are still skeptical, because they don't have data in pregnancy. They don't know, should we give this drug? If we give this drug, is the exposure going to be high? Is it going to be low? What is going to happen? So there is this great uncertainty. So the bottom line is that we don't have data on pregnant women using this drug. So what I then did was that I built a virtual pregnant PBPK model, and I used that model to characterize pharmacokinetics of naltrexone in pregnant population virtually. Okay, so here is like the model workflow that I used. As I explained earlier, I started by taking system parameters. I put it in the model, drug-specific parameters, I put it in the model, and then I use it to have a non-pregnant adult PBPK model. And then after that, I, refined the model and I validated it. I repeated the same step for intramuscular injection. And then finally, I added system-specific parameters, fetal placenta compartment, and things like that to develop the pregnant adult PBPK model. Now, as you can see, this is the final model structure. I represented all organs that we have in the body, including uterus and fetal compartment, just like we have it in pregnant women, okay? And here are some of the results from that validation step. As you can see, my prediction, which are those blue lines and the band, they perfectly match the observed data that has been reported in the literature, as well as what the FDA reported, okay? So once I am happy with this model, I believe I now have a pregnancy PBPK model. The next thing I did was then to conduct a virtual pregnancy pharmacokinetic trial. So in this trial, I administered a standard 380 milligram of naltrexone to 400 women before they become pregnant. And then after they become pregnant, I grouped them into 4, and I applied different doses during their pregnancy. So here is what the concentration time profile looks like before they get pregnant. So the goal here is that if I increase or decrease the dose, I want to make sure that the dose, the concentration or the exposure in pregnancy is at least similar to what I observed before they get pregnant, okay? Because if the exposure is higher, then that means there is risk for safety. If the exposure is lower, then probably the drug is going to lose its efficacy in pregnant women. So that is the reasoning for the comparison. So I performed all these simulations, and then I make all the comparison. As you can see, the pink are the mother's plasma, while the blue are the concentration levels in the fetus. So after I made all the predictions, all the simulations, I came up with the conclusion that in first and second trimester, if we reduce the dose by 25%, that is giving them 285 milligrams, then this is a good dose that will give us a reasonable exposure. Or if we are in third trimester, then we can try 50% reduction from the standard dose, which is 380 milligrams. So reducing the dose by 50% in third trimester to 190 milligrams, is going to give similar exposure to what we have before they become pregnant, okay? So I hope that this presentation has given you a valuable insight to begin to look at the possibilities, different things that we can do with pharmacometrics, especially population pharmacokinetics and PBPK model. And I hope you start to begin to look at PK modeling in a different way. So I want to appreciate everyone for their time, attention, as well as the opportunity to share this webinar information with you. So I would be happy to take any questions now. Thank you.
Thank you, Jide. This was quite very foundational, and I know that everyone who is here have really benefited from now we know the basics for pharmacometrics. There are quite a few questions already that came in through on the question and answer section. I will just maybe take them one by one, and we can quickly address them. I know that we are quite far behind schedule. We have taken a lot of time, but we will understand that from this, we see that he had to go very granular. So yes, that is highly appreciated. So there are a few questions here. If we can quickly just address that. The first one says, what does bioequivalence means as regards the model you're describing? If you can, there was a point where you talk about bioequivalence. Just a brief answer to that. I know that's not the focus, but we can address that.
Yeah, so bioequivalence is when there's a drug on the market and then a new company is trying to come up with an alternative, the same active pharmaceutical ingredient, but they want to call it a different name. For example, if you have paracetamol, we have different types of paracetamol on the market, one by M&B, one by other different companies. So if a new company is coming up with a new drug, a new equivalent, then you have to demonstrate bioequivalence. So, and that means that you are trying to show that the rate and extent, at which this drug presents in the body is similar between the two. So the application of model in this case is not always, we don't use model for bioequivalence. That's pure and simple. But there are some situations where model can come in. For example, if you are developing a drug for long-acting injectable, where the standard crossover study is not realistic, and you have to use parallel design, and then you need a lot of subjects, then model can be useful in that regard. Yep.
Thank you. Thank you for that. Another question is, if NCA is done already for a data set, in what criteria would there be need for compartmental analysis?
Great question. So, like I said, when you do non-compartmental analysis, the best you can get are those parameters from looking at the graph, like you can determine Cmax, you can determine Tmax, you can calculate AUC, for example. So these are the parameters that you can reliably estimate. Now, when we talk about important pharmacokinetic parameters like clearance, absorption rate constant, and the likes, you cannot get this result from NCA. So you need a model for this. Now, even if you use calculation to get your absorption rate constant or clearance, because I know there's a formula for clearance, dose over AUC, if a drug follows 3 compartment or 2 compartment, for example, the result of clearance from that model is probably going to be totally different from the result you will get from an NCA. Okay, so NCA clearance is going to be highly inflated. So if you want to know the true value of your clearance or the true value of absorption rate constant, then you need modeling. You need to go beyond non-compartmental analysis. Yeah.
Okay, thank you for that. Another question I might just have to pick because of our time. There's a question that says, for the naive pooled, are we to find the average to assume it is for an individual? The plot appears an individual data set is reckoned with out of the 5. There was that part where you were describing the different analysis.
Yes, I remember. So in naive pooled analysis, so I understand we have 5 subjects from what I demonstrated, but that's why I said it is an assumption. The assumption we make is that all this data that you are looking on this plot, even though they came from 5 subjects, we are assuming it came from just one individual. So if it came from one individual, then that means you can only fit a single line through all the data points because we are assuming it came from just one individual. So that's the assumption for naive pooled analysis. I mean, we don't generally use it. It's not popular in the population pharmacokinetic analysis world, but I'm just putting it out there that there's also an approach that we can use this. And personally, I use it in my project because it runs very fast. So I can do naive pooled analysis within 10 minutes. And then if I'm running one stage analysis, maybe one stage analysis is taking 40 minutes. So I can quickly do naive pooled analysis because of the simplicity in which I described it, so that I can quickly get what are the initial estimates that I can use, in my next modeling step. So, yeah.
Okay, thank you for that. Someone had asked what software is used for PBPK modeling. I might want to say that because we are still going fully into PBPK, we can keep that for next webinar. Is there a way we can widen our horizon in this area? Yes, that is what we are currently doing. If you will follow through, you will really get a lot. You will definitely, we are hopeful that at the end of this webinar series, you will be able to stand as a modeler yourself. So please, pharmacometrics was not defined. Is it the same with pharmacokinetics? I think they spoke to this a bit. If you can just do one more sentence for that. Friendship pharmacokinetics and pharmacometrics.
Yeah, pharmacometrics is basically it's a scientific field where so there's what we call clinical pharmacology, right? Where you describe what the body does to the drug, or what the drug does to the body. So pharmacometrics is simply the science of quantifying that process, quantifying what the drug does to the body or what the body does to the drug. So when you are quantifying it, then that's what pharmacometrics is generally all about.
Okay, I have Professor Chinedu Babalala here. We would like her to ask a question.
Okay.
Yes, ma'am.
Yeah, thank you, please. Sorry, let me lower what I'm doing here. I'm coming 1 second. So thank you so much for the lecture. You are too fast. You are Gen Z. It was really fast. So I hope we can get the recording. And I thank the organizers. I'm a professor of pharmacokinetics, and I usually like to learn new things. So when I started hearing, of course, we heard of PBPK and PK. But once I hear pharmacometrics, I said, well, I would like my students, expose my students to this. Recently, I was in ISS Africa too, and a whole day was devoted to this. So some of my students are already catching up with it, like Dr. Jacinta. I think Dr. Kutila also has taken some lectures in this. So it's good that you're running this series. I even asked my undergraduate students to join in. Now, I have a series of questions, and I would like to appeal that for the next one, if you could take us gently, that would be nice. And then if there's and once you start the practice, that's what I've seen about pharmacometric lectures. If we need to download software and things like that, come with our laptops and stuff, you let us know upfront so that we can have a hands-on. Now, even where I was trying to post questions, I'm trying to remember a few. The case studies you mentioned, enoxaparin. When you did it, where did you get? You said you collected data from born patients.
Yes.
So where did you get the levels of drugs? Did anyone do kinetics of them, or where did you get your data?
No, so therapeutic drug monitoring is done for enoxaparin. So
in the hospitals?
Yes, in the hospital. So I got it from.
What did they use to analyze this?
I think it's all this ELISA approach, and then what they measure actually is antifactor 10A levels, and then that is what we use as concentrations. Yeah. Okay,
that makes sense. So the other one, the naltrexone, the same question. Did you have any did you have any, will I say, parameters that indicated the drug exposure or levels?
Yeah, so that's a good question. And so the thing is that my goal, as I described, was to estimate the exposure of naltrexone in pregnancy. So right now, we don't have any data in pregnancy. So there's no way, that's why I did a systematic approach in the modeling. So if I go directly to building the pregnant model, then that means there's no data in pregnancy. How do I check whether my model predictions are right or wrong? So that is why I did not go straight to building pregnancy model for naltrexone. I started by building this first non-pregnant adult PBPK model for the IV dosing with my model.
Okay.
I was able to show that, okay, my model is doing very fine. Then I integrated intramuscular drug-specific parameters into the model so that I can switch from intravenous to intramuscular long-acting, which is what the pregnant women are going to get. Then after doing this, there's data at that step, and I also check my model at that step. So once I'm fine with these two steps, then it gives me confidence going forward that whatever I predict with my pregnant model is going to be true. And that is why what I showed here, those black data points are the observed data in IV and in IM, but non-pregnant.
Sorry, the observed data still virtual or still a model?
No. So those black dots are data from patients.
That you got online or in literature?
Oh, okay, I see where you're going. So I got the data from either literature or clinical pharmacology review submitted by the pharmaceutical company that developed the drug, because they usually submit their data and then you can always go into the database and pull the data. So I got the data from there.
Okay. Okay, so now when you say you've tested and it works, can you hear me?
Yes, I can.
Yeah. When you said you've tested it and it worked, is it because you have done some variation and the correlation, like, okay, if I vary dose, this is happening. If I vary this is happening. Is this what you mean?
Yes, because so what I mean is that I first want to know if the model that I have built is able to predict drug concentration of this particular drug. Okay, so that's why I started with IV. I built my model, and then I put properties of those drugs, naltrexone IV, into the model, and then I simulate. So as you can see, there's reasonable overlap of the observed black dots on my model predictions, which are the low lines. So then you can use some metrics like how many fold difference is your that observed data and predicted value varying from each other. So there's an acceptable range of 0.5 to 2. So if even though my model is not 100% superimposing on each other, there's still wiggle room of if it is between 0.5 to 2. Okay, so it's still acceptable. And then the question about variability. So the variability is intrinsically built into the model because you see, when I'm doing the simulation, I can say, okay, one set of subjects will be 20 years old, some of them will be 25 years old, some of them will have a weight of 80 kilogram, 90 kilograms. So there's going to be those variations in those virtual population parameters. So those variations are going to drive, that's why you can see that there are some kind of spread around the data, and it's not just a single line. So those things are what is making, and that is what we actually observe in reality. The difference from one patient to another might be because one has a different weight, one has a different age, so things like that.
All right. Of course, if there is genetic if there are genetic reasons, it would also indicate, I guess.
Yes, definitely.
There are genetic differences. Now, finally, when you were at the beginning, when you started talking about intrinsic clearance and all of that,
Yes.
you did mention that genetics was part. You were talking about intrinsic and extrinsic. reason.
Yes.
And you did mention that genetics was part of intrinsic, and I'm wondering, intrinsic is intra-individual. Can it be a source of variation? I thought that would be extrinsic, because the person that has a particular genetic profile remains that person.
Yeah, that's why I put it
know.
intrinsic. Because
Why is
intrinsic,
it intrinsic?
so intrinsic means, so let me start by saying within subject variability is imagine just a single subject. So I want to know if I take drug concentrations in this subject and I take drug concentration at another time, and these two results are different, what is causing the difference? So even if that subject has a particular genetics, between those two periods, that genetics would not change because we are dealing with the same subjects. So
correct.
That is within subject variability. Now, what I mean, I'm showing it on the slide, by intrinsic factor here, which is different from within subject variability. So, which is also different from intra-subject variability. So intra-subject variability is another name for within subject variability. So intrinsic here, I'm referring to as those covariates or factors of the patient that is outside the control of the patient. For example, if a patient is hepatically impaired, there's nothing the patient can do about it. Tomorrow, the patient cannot say, oh, I don't want to be hepatically impaired again. They don't have control of it. So the same thing with genetics, the same thing with their age, their gender, and what have you. But extrinsic factors are those things that, you know, we can ask patient to control it.
Okay, extrinsic can be controlled.
Yes.
Okay, again, what's the difference between, I'm sorry to ask that question, your POP-PK and PBPK,
yes,
are they not part of pharmacometrics?
Yes, they are.
Which is the broad-based terminology? Is it pharmacometrics?
Pharmacometrics.
We say, so under pharmacometrics, we have POP-PK and have PBPK. Yes. Am I correct?
Yes.
Yes. Pharmacometrics is the bigger name.
All right. Thank you very much for now. We'll be talking to you later privately.
Yes. At this point, I want to really appreciate everyone for participating in this webinar, the first in this series. We'll be looking up, as I mentioned earlier, that we want to really make pharmacometrics to institutionalize in Nigeria. So we are starting with this. We look up to for other series, and we at the end of this today, Pharmacist Ochuko will send in some questionnaire across the road to get some feedback so as to improve on this series, and we look up to your feedbacks and your suggestions. So I really want to appreciate everyone, especially our professors who have joined, Professor Balola, Professor Bolaji, and others that are on this. And other from diasporas that are on, I see several people from US, from Australia, and many others that have joined this webinar today. So I want to assure you that we are working towards having a face-to-face interaction and to really improve for answer. So we get across the road. We have some of our details in which we can get our information across the road. So we look up to you. By Pharmacist will give us the last information for the next webinar in series for Pharmacist. Thank you.
Thank you, everyone, for coming. So yes, as we've said, this is going to be a monthly series. Our next webinar will be on the 30th of April. That's the last Wednesday of the month. So you can set your calendars for the last Wednesdays of the month. So for this next one, we're going to be building on what this is an introduction, an overview. So we're going to be building on this for the next webinar on the 30th of April. Expect a mail that is requesting for your feedback from us very soon. And of course, the recording will be made available to everyone who registered. keep spreading the news. Pharmacometrics Africa, Nigerian chapter is here to equip us as pharmacometricians. So yes, at this point, thank you everyone for coming. And to the people behind the scene, thank you for holding the fort for us. See you in our next webinar. Bye.